Next up, we've got search insert position, LeetCode number 35. In this video, we're going to cover what, in my humble opinion, is the most important algorithm you can know when going into programming interviews. That's right, number 1. I won't keep it a secret, this algorithm is binary search. What binary search allows us to do is search through a sorted array in log n time. In other words, every time we have an array in a problem, we can potentially reduce time complexity by an entire order of magnitude, going from linear n down to log n. But first, to conceptually understand binary search, let's define this problem. Here's the definition. Search insert position. Given a sorted array and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. You may assume no duplicates in the array. The definition is fairly straightforward. We're just trying to find a number in an array like this. So with 1, 3, 5, 6, if we're looking for 5, well, it is in our array. So we just return the index 2. If we can't find the number, we're just going to return where it should be, so to speak. In that same array, if we're looking for 2, we'll return the index where it should be, which is between 1 and 3. So if we added it in there, it would be at index 1. Looking at our inputs and outputs, our inputs will be an array of numbers, which we're going to search through, as well as a target number, which we're looking for. And our output will be a single number representing the index where it is or where it should be. Our main edge case would probably be, what if we have an empty array? Well, we can just assume that would not happen for this problem. Due to the definition, we're also able to assume that we will not have duplicates in this input array. Alright, from covering problems like the two-sum problem, we already know what a naive solution is. In other words, there is a very obvious yet inefficient solution for this problem. For this one, that's to just scan through the list from left to right. Now the time complexity of this is O of n, because worst case we'd have to look at all the items in the array. So for this problem, that is something you'd want to acknowledge before moving on to the more efficient implementation. And for this efficient implementation, we're going to leverage the binary search algorithm. We set it up with 2 pointers that represent the ends of our array. Like a loop, these pointers are represented by a numerical index, in this case 0 and 3. We can also call these pointers low and high. Now what we want to do with binary search is cut our array in half over and over again. The way we do that is by looking at the value in the middle and then determining which half the value we're looking for would be in. Given that we have a sorted array, if we check the middle and our target value is greater, then we know it's going to be in the right half, if it is in our array. If it's less, we know it's going to be in the left half. So let's say we get our mid pointer by averaging the indices of high and low. We can round this down and get index 1. Okay, what we're looking for is value 5. We check the mid value and it's 3, which is less than 5. So we know if this value's in our array, it's to the right. So we'll cut our array in half by moving our low pointer to 1 after our mid pointer. The 1 after part is critical because first, we've already checked our mid, so we don't need to check it again or leave it in our array we're searching. And if we don't do this, we could end up with an infinite loop. So with our new low pointer position, we repeat the process. We find the mid by calculating the average of low and high, then rounding down. So in this case, our mid is equal to our low pointer. Now when we check that value, it's equal to the one we're looking for. So we can just return that mid index at this point. So this works great when our target is in our array, but what if it's not? Well, in a normal binary search, we would return -1 or index not found. But in this problem, we want to actually return the index where it should be. This is one of those cases where it really helps to draw out an example. We'll start over setting our low and high pointers to 0 and 3. Like last time, we calculated mid by averaging the low and high indices, and from doing that, we get 1. And this is of course also rounding down. We check that value, which is 3, greater than our target. So we know we're going to want to look to the left. So we move our pointer to the mid minus 1 or 0, and now both our low and high pointers are at 0. So in this application of the problem, we actually want these pointers to continue one more after our pointers meet. The simple reason is because we're rounding our mid down. When our index is not found, we're actually going one past where we need to be. This resolves itself if we just let our pointers actually cross instead of just meet. You'll notice in the final iteration of the loop, our left pointer will move across the right pointer and end up exactly where we want it to be. This last step is a quirk of this problem that sort of ruins the elegance of binary search, but it demonstrates why it's important to draw both possible cases of this problem, found and not found. Anyway, instead of waiting until the end, let's briefly talk about time complexity of binary search right now. This is going to be the first time we see logarithmic time complexity, and don't worry, I'm not going to make you calculate logarithm like math class. Log is effectively the inverse of n squared or quadratic time. So while quadratic increases at an increasing rate, log is increasing at a decreasing rate. Think about it this way, we're cutting our array in half every step. If we represent this cut by an iteration of the loop, then an array twice as big would only take one additional iteration before it's the same size. Because remember, we're halving it, so we're going half, half, half. Where a linear solution would add a additional iteration for each additional array item, log solution, binary search, has to double the items before adding a single iteration. I hope now you can see why this is an order of magnitude more efficient than a linear solution. So at this point, we more or less understand how binary search is supposed to work. So we'll use that to search, but remember the context of our problem. If we don't find the value, we want to return the index where it should be. Here's the pseudocode to do that, but this problem is a bit tricky because it's easy to write an infinite loop as well as because of that pointer crossing thing. So try it if you want, otherwise we're going to dive into the code right now. Okay, with that thorough definition of binary search covered, let's code out search insert or search insert position. Now we've got our two arguments, nums, an array of numbers, and target, the number we're looking for. With our understanding of binary search, the first thing we'll want to do is declare low and high pointers. Low will set equal to 0, or the first index in our array, and high will be equal to the rightmost index, or the length of nums minus 1. Next we'll write a while loop, while low is less than or equal to high. Because remember that special case of that final iteration, then within the while loop, all the action is going to happen. Remember, we're going to look at our mid index over and over. So we need to calculate our mid index based on the average of low and high. So I'm going to declare that variable mid and get it by taking the average of high plus low over 2. And then to round down, we'll use the math.floor function. Now, the next thing I like to do, just to be clear, I like to take the value out of our nums array at our index mid, and I do that and store it in a variable midval. So we just use direct indexing with the index of mid. Okay, now we have 3 possible cases. Midval is equal to our target, the midval is less than our target, or it's greater than our target. So let me just write that out. If target is equal to midval, that is, the midval is the number we're looking for, then we can just return mid, which is our middle index. So we found the number, and we return the index we found it at. Else if target is greater than midval, we know that if it's in our array, we want to search to the right. So remember, we just represent this cut by moving our left pointer to the right, or our low pointer to the mid plus 1 index. So low equals mid plus 1. Otherwise, our target is less than our midval or too high, so we want to search to the left. So we set our high equal to mid minus 1. Now, if our loop breaks and these pointers not only meet but cross each other, then we have to return one of our pointers. That is the pointer where our value should be. And if you remember our examples, this was the low pointer because of the special case of the last iteration of our loop. Let's just step through another example so we're extra clear. This time with the code as reference up top. Okay, now the time complexity for this one. Well, we've already described that binary search is log time complexity because we're cutting the array we're searching in half over and over. Now, in terms of space, we're just using the pointer method to store a few numbers that represent indices. So we just need a number for low and a number for high, and then some temporary values inside the while loop. For that reason, we're going to be using constant space. In other words, our space does not scale with the size of our input. Binary search is an algorithm that's so useful, you should definitely have a solid grasp of it conceptually, and you should be able to code it pretty confidently. I'd say some variation of binary search is in the top 3 most common phone interview questions, and it's often used to weed out programmers who know what they're doing from those who don't, even entry-level programmers. So I can't stress enough that you should really have this one down.